talking about online scheduling. As Amit mentioned, I have worked primarily in the area of approximation algorithms, but this is not going to be about approximation algorithms. This is work that me and Amit and some of our PhD students have done over the last 5 years. So since the Bhatnagar Award is about work in the last 5 years, I felt it was appropriate to talk about this. So this is a quick overview, and I'll keep showing you a slide like this one at various points in the talk. So I'm first going to talk about online algorithms, for those of you who do not know about that. And then we'll talk about scheduling on a single machine, scheduling on multiple machines, with speed augmentation, with rejection. And finally, I'll say something to conclude. So suppose you are a company which makes washing machines. Okay? And your washing machines are bought by people around the country. You have, let's say, 2 service teams, and their task is to service maintenance requests that arise, right? So a washing machine breaks down, and then you as a company have to send some repairman or a service team to attend to that request. So ABC is the name of the company, and it has 2 teams. Let's call them T1 and T2. Okay? Now you have a very simple problem. You have to figure out which team should service that request. Right? So a request will come. Let's say all the cities are located on a line. Right? So we are mathematicians. We like to abstract everything out so that till the point that it does not make any sense. So let me assume that everything is out there on a line. The cities, the requests are going to arise on that line, and the service teams are also sitting on the line. Okay, so the first request arises at that point. The requests are denoted by R, and I would send one of the teams to service it. Let's say I decide to send T2 to service that request. What do you think the objective should be here? What is it that we should be trying to do? Right? Of course, we want to service all the requests, but we should try and minimize the total distance that my teams are traveling. Okay. So T2 serves that request. Okay, good. Now another request comes. Well, makes sense to send T1 there. Let's do that. And the arrows are showing the total distance that my teams have traveled. Right? So essentially, the sum of the lengths of the arrows is going to be my measure of how good I've done, how well I've done. Okay, another request arrives there. I should send some other team. I should send one of these 2 teams. Let's say I decide to send T1. Okay, to service that request. Now at this point you must be worried, right? Why did I send T1 there? Right? T2 is so much nearer. Why didn't I send T2? Okay, that's justified. Your worry. And let's ask that question. So that's the whole question. That's the policy we have to decide on. Which team should we send? I seem to have made some stupid decision here. Was that the right decision? Okay, so that's the entire problem. What team should I move? Which of these 2 teams? So a natural strategy is what one would call is the greedy strategy, right? What you all would think right away. Just move the team which is nearest to the place where the request arose. Right? How difficult can that be? Okay. We will assume that we know nothing about these requests. In fact, we will make our life difficult and assume that there is someone who is out to make us look bad and adversely, who is generating these requests. So he or she will generate the requests in such a manner so that our algorithm looks really, really bad. Okay? So let's come back to my example, and now let me show you how this request could be generated. So we are following the greedy policy now. The request shows up there. The greedy algorithm would say that I move T2. Yeah? So it travels 10 units. So those are the distances. It travels some 10 units and services the request. Okay? So it services that request. Now a new request arises somewhere in the middle. Again at distance 10 from T2, but a distance 20 from T1. So which team will you send? T2. Okay, so T2 reaches there, services the request. Now you know what I'm going to do next? Yeah. So again the request comes with the same city as before. Okay, what will it do now? Move T2. Okay, you moved him another, or you move that team another 10 units. What next? Again the request is going to come in the middle, and again you will move T2. Right? You have one team which is lying idle. It's slightly further away, but it's not doing anything. You can see that every time a request arose, one of my teams had to move 10 units. So in particular, if n such requests were given, then this greedy algorithm will incur a total distance, a total cost of 10 times n. Everyone with me? Any questions? Okay, good. So n requests, greedy travels 10 times n. Now, you must be wondering, is there a better way of doing this? Of course, right? Almost everyone can perhaps see what is the better way of doing this if I knew what the feature requests were. Suppose I told you where the requests were arising in the future. Okay? What will I do now? The moment the first request comes, which team am I going to move there? T2? Why not just move T1 all the way there? Yeah? So now the next request is coming at where T2 is. T2 can serve it without moving. The next request is going to come where T1 is. T1 can serve it without moving. And so the total distance that my teams travel for the entire sequence of n requests is just 30 units. Okay? So at this point, I can now introduce some terms to you. So this algorithm is what's called an online algorithm. What's an online algorithm? An algorithm which has to serve some requests, has to make some decisions, except that it doesn't know what the future requests are. So the algorithm that was deciding which team to move, that's an online algorithm. It has to make a decision, but it doesn't know what the future has in store. It doesn't know where the requests are going to go. We would like that the total distance that my online algorithm travels for this particular example, for this particular problem, is not much more than the best solution. Okay, now what do I mean by the best solution? So we call that an offline algorithm. We'll say, suppose I knew all the future requests, right? Then I can compute what is the best way to serve those requests. Right? I'm not worried about the computational aspect. I'm saying, I give you the entire sequence and now you can figure out the best way of serving all of these requests.
Yeah,
I want whatever that number is. In that previous example, that number was 30. I would like to serve these requests. I would like my online algorithm to serve those requests such that the distance it travels is not much more than 30. Of course, I will have to pay a price. I don't know the future, so I can't be expected to serve the request within 30 distance. I will have to pay more. I will have to travel more. But I don't want it to be much more. I want it to be a small multiple of the optimum value. And that small multiple is what we call the competitive ratio. Okay? So I would like that my online algorithm, in the worst case, never, for all possible request sequences, it never travels more than, let's say, 15 times the best solution. And then this number 15 will become my competitive ratio. Okay? So for instance, let's look at what the competitive ratio of the greedy strategy we just saw was. Okay? So the greedy strategy, for a request of length n, I traveled a total distance of 10 times n. Right? For every request that came, one of the teams had to move 10 units. So 10 times n is the total distance traveled by greedy. And if some algorithm knew the entire request sequence, then it had to just travel 30 units. And so the ratio is just n by 3. And n by 3 is a bad ratio. Why? Because it becomes unbounded. If I had 1 million requests, then I am worse off than best solution by a factor of roughly a million, of 1 million by a 3. Right? That's huge. We don't want something like that. So whenever we have a ratio which looks unbounded, which can be increased up into 3, we say that that is a bad algorithm. We don't want such online algorithms. The whole purpose in designing online algorithms is to come up with an algorithm whose performance can always be bounded. Right? It doesn't ever grow in these rapid manners. Okay, so now you must be wondering, okay, can I do anything better, or it's just the nature of this problem that nothing can be done here? Surprisingly, there is a very simple algorithm. It's called balance. We like to give names to our algorithms so that we can keep referring to them. So this algorithm is called balance, which for this problem does very well. Okay? In fact, it is 3 complicated. Now, just to remind you, what does it mean? It means that the distance traveled by this algorithm will never be worse than 3 times the best way of serving those requests, even if you knew all the requests in advance. Right? So in some sense, the price for not knowing the future here is just 3 and not more than that. So what is the algorithm? Again, the algorithm is very simple. If the request arrives on the same side, right, there are just 2 servers, these 2 teams. If the request arrives on the same side, then move the team which is closer. If the request arrives in the middle, then you do something strange. You actually move both the teams towards the request. Right? Now you're going to say, well, this sounds stupid. Right? If I'm moving both the teams towards the request, I seem to be doing only more work than I would have done if I had just moved one team towards the request. Yes, I seem to be unnecessary. So maybe the request is 5 units away from one team and 15 units away from the other team. I will move both the teams 5 units towards the request. And yet I'm saying this is a good algorithm. And let's just see how it performs on the previous example of ours. Right? So team 1, team 2, same starting position. Now to remind you, the first request is going to arrive at the very end. What does the algorithm do? When it arrives at the same side of both the teams. So it is going to move the closer team to the request. So T2 will move to R. Now the next request is going to come in the middle there. What happens now? Both the teams are going to move 10 units towards the request. Okay? Now you see what's happening. Right? The next request comes, again 10 units to the right. Which team will move? By your rule, T2. Okay? Next request is again going to come in the middle. Which team would move? Both teams would move now and will come at that point. Now once again the request is going to come to the right. Actually both the teams are equidistant now, so I can move any one team. So let's say I decide to move the green team. And now I'm done. Why? Because the subsequent requests are going to come where T1 is. And it can serve it without any penalty. And then the next request is going to come where T2 is. And it can serve it without any penalty. And so on and on. Right? So what seemed like a stupid algorithm actually works very well for this request sequence. But I'm not saying it just works well for this request sequence. I'm saying no matter what request sequence you give, and that's what worst case here means. No matter what request sequence you give me, or give this algorithm, it has no knowledge of the request sequence. This algorithm will never do worse than 3 times any algorithm which even knew the entire sequence in advance. It's a really powerful statement. And just to show you what is the total distance we traveled, okay, if you've been following, you can check that computation, but even otherwise, trust me, that the total distance the two teams traveled is 70, which is less than 3 times 30. And why 30? Because the optimum was actually 30. Right? If you knew the entire request sequence in advance, you could just have moved the first team, T1, to the request and be done with it. So, this was just to give you a flavor of online algorithms. There's a vast literature on online algorithms. It's not a very old area in algorithms. It started only in the 80s with some seminal work by Manasseh et al. And they were mainly interested in problems of this nature, what are called K-server problems, but also in paging, right? So it's a very, in a computer system, the main memory of the system is limited, right? And most programs, most processes require a huge amount of memory, much more than what the system provides. So the way it is implemented is that if it needs memory, it brings a page from the secondary memory and replaces one that sits in the main memory. And now you need to decide what to replace. Okay, so if you don't know that, it's okay. So a few things to keep in mind. One is we make no requests about the request. We make no assumptions about the request sequence. And that's why I'm stressing on the word adversary. We would say that the requests are generated by an adversary, someone who really wants to beat our algorithm. Okay? The competitive ratio is computed for the worst possible sequence. Right? You don't just look at your favorite sequence and then compute the ratio on it and say, oh, my algorithm is too competitive. Over all possible request sequence, you would look at how poorly your algorithm performs compared to the best and then compute it. So in that sense, it is akin to what's called the worst case analysis of algorithms. Clearly, an algorithm which has a small competitive ratio is better than an algorithm which has a large competitive ratio. And in some sense, it measures how sensitive our algorithm is to future requests or to future inputs. So, I'm now going to start talking about scheduling. And just as a quick recap, what we said was an online algorithm has to make decisions without knowing future requests. Requests are made by an adversary, and competitive ratio is the ratio of the performance of our algorithm to the best algorithm which knows all the requests. Okay, on to scheduling. So let me first tell you what machine scheduling is, because when I type scheduling into Google, it comes up with very strange pages where I'm trying to schedule, usually lots of calendar-like images where you're trying to build your daily schedule, right? How to. So when we talk of scheduling here, it's slightly different. Scheduling here means that you have some tasks, some jobs. There are some resources, which we'll also call machines, and you have to assign those tasks to those resources, right? Those tasks could be, projects. The resources could be people. The tasks could be programs in a computer system. Resources could be the processors. Actually, scheduling originated in the operations research community, and there the tasks were the actual jobs that you have to machine a job. You have to put it on a lathe machine. So the machines or the resources were actually physical machines, lathes, or the various kinds of machines that are there in the workshop. So, so it originated in the OR community, but now it's a very important part. This discipline is a very important part of computer systems. So a scheduling algorithm is an online algorithm by its very nature, because it has to make decisions on, a job arrives, it has to make a decision on where to put the job without knowing about what is going to come in the future. Okay, so let's see. I'll begin by just talking about scheduling on a single machine. Right? There is a single machine. How easy can it get? There is a single machine, and there are jobs that arrive over time. When a job arrives, I'm going to make this simplifying assumption. When a job arrives, the scheduler knows how long the job is. By long, I mean how much time it will take on the computer system. How much time, how much processing it will need. Okay? And the scheduler has to decide what order to process the jobs in. Okay, so on the right, the font is slightly smaller. There is like a running commentary of what is happening. So in case you miss what I say, you can also read it on the right. So at time 0, we have two jobs that arrive, a red job and a blue job, each of which is of length 1. Okay? Let's say the scheduler decides that it will first do the red job and then it will do the blue job. Okay? And then it has processed for times 0 to 2, it has processed these two jobs, right? What does that mean? This means that the machine has finished processing the red job from time 0 to 1, and then it has finished processing the blue job from time 0 to 2. At time 2, another job arrives, a green job, which is of length 3. Okay? Well, there is no decision to be made here really. The scheduler just decides to schedule this job and put it on the machine and starts processing it. Well, there is no other option but to process that job. And so from time 2 to 3, it processes this job. Okay? At this point, 4 other jobs arrive. At time 3, 4 other jobs arrive. Okay? Maybe what the scheduler does is it just puts these jobs at the end of this queue. And so from time 3 on to time 5, it will finish processing the green job. And then from 5 on to 9, it will process the remaining brown jobs and get a schedule. Okay, so this is what a scheduler is supposed to do, and this is what a schedule is, right? In what order it processes the various jobs. So there is a notion of a release time or an arrival time of a job. When the job arrives, reaches the system, you submit it now, and then the system returns the job to you 3 hours later. So your response time, or the response time that you're seeing, is 3 hours. Right? What would be a good scheduler? It would be one which would try to minimize the total response time, right? That could be one metric. We call these response times flow times, and the flow time of a job is just the difference between the completion time and its arrival time. It completes at a certain time, it arrives at a certain time. This difference is its flow time. And so these green arrows here, not the green arrows, these arrows here denote the flow time of the jobs. Right? So the red job was released at this time and it finished at that time. The blue job was released at this time and it finished at that time. And so the total length of these arrows is the total flow time of the schedule. And you can compute what the total length is, and it's 24. Okay? Now, one other way of thinking of flow time, or if I have to compute the total length of these arrows, one other way of doing it could be that I look at any point and I see how many arrows cross that point, right? Which is the same as how many jobs were released before that point and have not yet finished. Okay? So if U denotes the number of unfinished jobs at a time t, then flow time can also be thought of as the sum of this quantity over all times. Okay? This is just a useful alternate view of flow time, which we'll need later. Okay? Good. So I built a schedule and I said this is my measure. Now, given that this is my measure, is this the best schedule I could have built? Could I have done something better? Right? Again, we are in the world of online algorithms. We have these jobs arriving. We need to decide what to schedule. We have no knowledge of what is going to create. So, turns out I could have built a better schedule if you allowed jobs to be preempted. Right? If you allowed a job to be stopped and restarted. Okay? So this should be intuitively very obvious to you, right? Suppose you are standing at the checkout counter of a store. Okay? You have bought 6 bananas, right? This happens to me all the time at Shuffle. Right? I have 6 bananas in my hand, and the person ahead of me has 2 basketfuls of vegetable. Right? Suppose there were not just me standing with 6 bananas, but there were 5 other people standing behind me with 6 bananas each. Now, what would be a better way of scheduling? Now, the measure is the same, the wait time, how much time we will take to get out of the store. It would be so much better if whatever, I forget, I think it's called Sanjay, the Safal storekeeper, if he would say that, oh, these guys are smaller jobs, right, which means the 6 bananas are the smaller jobs, let them get ahead of the 2 basketfuls of vegetables, right? Of course, it is incorrect, impolite to do it, and but this is not true for a computer system. In a computer system, I can always stop a large job and let smaller jobs get ahead, right? Why is that better? Assume that the 2 baskets full of vegetables takes 10 minutes to check out, and the bananas take 1 minute each to check out, or the 6 bananas, right? So the 5 people who are standing with 6 bananas, they will be waiting for a total time of 5 times 10, 50 units. While if I had moved this person with 2 baskets of vegetables, I have nothing against it. Sorry, if you got it wrong. I'm just trying to illustrate a point here. So if you moved him behind, then he, of course, has to wait slightly longer. But all those people who had small jobs, they will wait much, much less. And so the same thing is happening here. You might be running, the green job that you are running is a long job. If short jobs arrive, it makes a lot of sense to preempt this big job and bring it back later when things are quieter. Okay? So you can check if you can do that computation very quickly. So what have we done here? So the green job is getting preempted here, and I'm continuing it later. So its flow time or its response time, it was released here and it goes all the way. So its response time is now 7 minutes. But all these brown jobs, their response times have come down significantly, right? And that helps. And actually this is better. And so the question then is, what is the best policy? Again, what would be the right thing to do? And the best policy, as you know, almost all of our students in computer science would know by now, is what's called SRPT, which stands for shortest remaining processing time first, which is what I just described to you, right? At each time, schedule that job whose remaining processing time is as small as possible. Okay? So let's do this with an example. I have 2 jobs, same example as before. So I have 2 jobs. At this point, both of the jobs are of the same length, so I can schedule any one. I decided to schedule the red job. Now, at time 1, the red job is over, and only the blue job remains, right? So I have no other option but to schedule the blue job. At time 2, this green job arrives, long 3-unit green job. I have no other option but to schedule it. And now, at time 3, remember what was going to happen? 4 brown jobs arrive. Now here is an important decision. At this point, what is the remaining processing time of the green job? It's 2 units. That's the remaining time I need to process the job. The brown jobs all have a processing time of only 1 unit. So what's a better thing to do? Right? We will preempt the green job in 4 and schedule one of the brown jobs. Any one of the brown jobs, because they are identical, they have the same processing time. So I schedule one of the brown jobs. Still, at this point at time 4, the brown jobs are still better than the green job. So I'll schedule one of the brown jobs and another brown job, and now finally I'll schedule the green job. And this is optimum. What that means is that any algorithm which knew all future requests will not be able to beat this in terms of where the metric is the total response time or the total flow time. This is the best algorithm possible. Right? So this algorithm doesn't require knowledge of the future. What I'm saying here is that even if you knew the future, you could not do anything better than this algorithm. So this is sort of the holy grail of online algorithms, if you can find such an algorithm. But it's very hard usually. This is short proof. There are proofs available for this. Yes. Yeah. So every time I say something which is a theorem, there is a proof. right? I don't say theorem without proofs. And sometimes the proofs are 2 slides and sometimes the proofs would be 20 slides, but I'm not going to show any proofs today. Yeah? Okay, fairness. Okay, this is the optimum way of scheduling jobs if I have a single machine. But is this fair? Right? We should also ask this question. I have minimized the total waiting time or the total response time of the jobs. But could it be the case that I'm penalizing some job too much? Right? For instance, let's look at the same algorithm I told you about, SRPT. And suppose I have 2 jobs now, a red job and a blue job, and this blue job is unfortunately just slightly larger than the red job. Just slightly larger. Okay? What's going to happen now? I'll schedule the red job. At time 1, another red job comes. Same size. What will I do now? I have a red and a blue. Blue is slightly larger than the red. I'll again schedule the red. Time 2, same thing repeats. Right? And the blue, the bichara blue is stuck there, right? Because it's just slightly larger than the red. So I can continue like this forever. Right? The red jobs are all seeing a response time of 1, best possible. The moment they arrive, they're scheduled and finished. The blue job is seeing a response time equal to the total number of jobs, in fact, which could be 1 million jobs. Yes? That's very unfair. This is the optimum algorithm if you wanted to minimize the total waiting time. The total waiting time is minimum here, but it's not a fair algorithm. Okay? And so how can you bring in fairness? Right? So what do we have here? We have the response time of the first job, the response time of the second job, the response time of the third job. We really have a vector of response times. And I want a single scalar as an objective. And I'm mapping this scale, this vector. I'm saying, okay, let me sum up the entries of this vector. That's the total. Right? I'm calling that the total response time or the total flow time. I'm trying to minimize that. But if I want fairness, I should not just look at the one norm by just taking the sum. I'm looking at the one norm of this vector. I should look at higher norms. I should look at 2 norms. If I had done a 2 norm there, I would not get the problem. Blue will be served very quickly, in fact. Right? So it makes sense to look at higher norms. The pth norm, for instance, if f sub j denotes the flow time of job, flow time or the response time of job j, so that's just f sub j to the p summed over all j to the 1 over p. And that ensures fairness. And whenever you have something interesting, there is a theorem which says it cannot be done. Right? And so there is a theorem by Azar which says that there cannot be any online algorithm to minimize the p norm of flow times. When I say there cannot be anything, what it means is आपने कोई भी online algorithm लिया, उसकी competitive ratio unbounded होगी. Right? Remember, हमारा जो greedy algorithm था 2 teams वाला, उसमें competitive ratio n by 3 थी. n infinite हुआ, competitive ratio infinite होगा. Same will happen here. P between 1 and infinity, strictly more than 1, because p equals 1 we can do. P equals infinity also we can do. And those of you who are getting bored can look at the last line and figure out what the algorithm is. So P equals infinity also one can do. But any finite P, not possible. Okay? What other measures might be interesting? One very interesting measure is stretch. Right? If I have a large job, let's say of size 100, and I have to wait for 200 units, that's okay. So then that means that I'm incurring a stretch of 2. Right? I'm looking at the ratio. So if all jobs are incurring a stretch of 2, it would be fair. Right? Stretch of 2 क्या मतलब है? A job which is of length 1 will incur a flow time of 2. A job which is of length 100 will incur a flow time of 200. A person who has a large shopping cart, a shopping cart filled with a large number of goods, should wait longer. Someone who has a small basket should weigh less. Fair. That's another metric, max stretch. Again, you cannot optimize. Or it is possible now, but the bounds are slightly worse. So you cannot achieve a competitive ratio better than P to the roughly square root P, where P is the size of the largest job. Okay? So just saying that the bounds get worse. It's not as bad as the previous one, but it's still bad. Okay, so I'm now going to move on to multiple machines. If there were any questions to this point, it's a good time to ask. Yeah. After flow time, so when you take a big job and you break it up into multiple 1 unit jobs, then what happens is that the flow time measure changes. Right? Why? Because the first unit, suppose the first unit finished at time 10 from 0, the second unit finished at time 11, and third unit finished at time 12. Now you are not counting 10 plus 11 plus 12. If you think of them as 3 small jobs, that's what you will end up counting. You want to count it as just one job, which is, you want to count it as 12. So that's why that transformation is not. Okay, so a quick recap. Flow time is just arrival to completion. SRPT is the optimum way of scheduling jobs if you have a single machine and you want to minimize total flow time. And any other interesting measure when you want to bring fairness in becomes hard. Okay, multiple machines. So single machine was just really a toy problem, right? Most modern computer systems have millions of processors. Okay? And a job that is coming in is being scheduled on, usually it comes with some restrictions, right? What I mean by that is that it cannot just be scheduled on any one of those million processors. Quite often the restrictions have to do with the software that is installed on that particular system, or security policies, or many other things. So we'll assume that a job that comes in can only go on a subset of the machines. Okay? That's what I mean by a heterogeneous system. And what happens now? So a job arrives, let's say it arrives at, there's usually a notion of a central scheduler. And the central scheduler will decide which machine to put the job on. So the 4 lines here are the 4 machines. Okay, these jobs that I've shown here are the queues associated with these various machines. Right? So this machine has these jobs on it. This much of the queue has already been processed on the left. These are the jobs remaining on the second machine, and on the third machine, and on the fourth machine. Okay, a new job comes, it has to be assigned to one. Suppose it's assigned here. We will assume that each machine is following the SRPT policy, which we know is the best policy. And so each machine will keep its queues organized in increasing order of processing times. Okay, now I'll quickly show you an example that when you have heterogeneous machines, again, it's not possible to get a bounded competitive ratio. And the example is quite simple. Suppose you have these 3 machines, right? These 3 horizontal lines are the 3 machines. And I will have 2 kinds of jobs. A red job and a blue job. The red job can be scheduled only on the top 2 machines. The blue job can be scheduled only on the bottom 2 machines. Okay? Everyone understands the picture? And now I'm going to release some jobs, and I'm going to release them in a specific way so that no online algorithm can do well. Okay, what's this way? At every time, I will release 2 red jobs and 2 blue jobs. Well, the processing power that I have available is only 3 units, so which means that 3 of those jobs can be scheduled of the 4, and 1 will have to remain waiting. So suppose I decided to keep a blue job waiting here. The same picture repeats at the next time. Again, 4 jobs get released, 2 red, 2 blue. Well, you might have a really sophisticated online algorithm in mind. Maybe it decides to, so it will also, again, 2 jobs will remain waiting, right? Because 1 from the previous step and 1 from this step. Maybe 1 is red and 1 is blue. We keep doing this for t time units. Whatever is the online algorithm, whatever online algorithm we think of, it will have T jobs remaining at this point in time, right? Just by simple processing, how much jobs can be processed well. And some of those are red. Let's say there are R red jobs remaining and there are B blue jobs remaining. So R plus B is capital T. And so one of these two quantities is at least T by 2. Right? The sum of these two is T, so one is at least T by 2. Let's say the red jobs that are remaining is at least T by 2. Okay? What will I do now? I have at least T by 2 red jobs remaining. Now, the adversary. So who's deciding on what job comes at every point? It's the adversary. The adversary is now going to release 2 red jobs. Okay? You will schedule them on these machines. Again, it will release 2 red jobs. You will keep scheduling them. And what would you do? The last machine can be used to finish off the blue jobs that you have accumulated. But the red jobs that you have accumulated at time t, that are not going away anywhere. Those are red jobs that you have accumulated will remain with you till the end of this. And so even at the end of this, let's say at time t plus L, you have R red jobs remaining. Okay, why is this bad? What is the flow time of this schedule? Now here I want you to recollect that I said flow time can also be thought of as the number of outstanding jobs, unfinished jobs at every point. At each of these L time units, I have at least T by 2 jobs waiting. Yes? So I will forget about everything else and say that the flow time of this schedule is at least T times L by 2. Right? Because there were T by 2 jobs at least remaining here and each of these L time steps. Suppose you knew what the future was. What would you have done? Suppose you knew that at this time, from this time onwards, I'm only going to get red jobs. What would you have done? Right? You would have finished off all the red jobs before. Remember, at each time step, you are getting 2 red and 2 blue. Potentially, you could have serviced both those 2 reds at every time step. So that at this time, you had no red outstanding. You had some blue outstanding, but those blues could then be serviced here. Right? Now, so I'm not talking of any specific online algorithm here, note. I'm talking of any online algorithm. The online algorithm, the only thing the online algorithm doesn't know is which kind of jobs the adversary is going to release at this time. If there were more blue jobs outstanding at this time, then the adversary would have released blue jobs here. Because there were more red jobs outstanding here, it released red jobs. And now, what you can check very easily is that the flow time, the optimum flow time, will be something like L plus some function of t. Why would it be L? Because here, for this long, we are thinking of L as much, much larger than t. Right? So for each of these times, I will incur 1 unit of flow time or 2 units of flow time. So it will be 2 times L plus a function of t, some t cube or some such thing, which I'm not computing. And then, if you look at the ratio of these 2 quantities, again, think of L as much, much larger than t. Here, L is getting multiplied by t by 2. Here, it is getting multiplied by 2. The ratio is roughly t by 4. What does that say? If t was 1,000,000, then I have a competitive ratio of 1,000,000 by 4. By I mean any online algorithm. Right? So, this in fact is a proof for this theorem that I have here, which says that there is no online algorithm which minimizes flow time on heterogeneous machines. Right? So, here it is important that some jobs can be processed only on some subsets of machines. So, if I'm minimizing flow time on heterogeneous machines, then there can be no online algorithm for it, or no online algorithm with any bounded competitive ratio. So what do we do? And this is actually some of our major contributions over the last few years. We look at what is called resource augmentation. We say, okay, the online algorithm doesn't know the future. Let's give it some more power By power I mean, let's say that our online algorithm has speeds which are an epsilon fraction faster than the adversary, the speeds of the machines that the adversary has. Okay. Just epsilon. So that's what we say there. And so for epsilon is 0.1, then our machines are 10% faster than the adversary's machine. And or equivalently, you can think of the adversary machines as 10% or roughly 10% slower than my machine. And if I assume such a thing, then we can get a competitive ratio. So with this model, this is called the resource augmentation model. And in this model, a very simple algorithm actually works now. Okay? And what's the simple algorithm? It's all here on the slide. When a job comes, the scheduler has to dispatch it, has to send it to one of the machines. Right? That's a critical decision. Once it is decided on the machine, then for the machine, the right policy to follow is SRPT. We already saw that. Yeah. So the critical decision is which machine should this job go to? And we will just follow the greedy rule. What does the greedy rule here mean? Right? If I put the job on this machine, let me calculate how much the flow time increases by. If I put it on some other machine, let me calculate how much the flow time increases by. If I put it on a third machine, let me calculate how much the flow time increases by. And on whichever it is the least, I'll put the job on that machine. Okay? So let me just illustrate it very quickly, and I think, so suppose this was the current picture. A new job arrives. It has length 2.5. Okay, so just to aid you, this is 1, and this is 2, and this is 3. Right? I have not put numbers, but should be sort of clear. And suppose this new job that is coming can go only on machines 1 and 2, which are the top 2 machines. Okay, so it tries to go on machine 1, or it doesn't actually do this, it's the scheduler which is doing this. And the scheduler will compute what is the increase in flow time because of this. And what it finds is that if it had to go on this machine, it would go between this job of 2 and job of 3, so it will have to come here. And so the increase in flow time one can compute is 10.5. Why? Because these two jobs will have to be moved right, and this will incur a certain flow time, which is 2 plus 1 plus 2.5. 5.5 would be its flow time, and these two guys will have to be moved right by 2.5 minutes, so that's what we get. Okay? Remember, it can go on machines 1 or 2 only. On machine 2, we find that the increase in flow time is 12 minutes. So where should this job go? Machine 1. So it's scheduled on machine 1. This is the entire policy. Okay, so I'll quickly illustrate it on one more example. Suppose a new job comes which can go only on machines 2 and 4. So once again, for machine 2, we already saw that the increase in flow time is, and it's the same size as the previous job. So it was 2.5. So here the increase is 12. And on machine 4, the increase is 12.5. Because this is where the job would go. It has length more than the third job, this job, and smaller than this. So it is where it would go by the SRPT rule. And so the increase there is 12.5. And so this job should go on machine 2. And so it will be scheduled. And that's it. And the big theorem that we proved here was that this policy is a 1 plus 1 by epsilon competitive. Or this algorithm is 1 plus 1 by epsilon competitive. So just to put in numbers, if epsilon was 0.1, I was assuming my machines were 10% faster, then I get a 11 competitive algorithm. Right? And we also have results which say that this is roughly the best you can do. And surprisingly, that we can use this idea to also work with the p-norm. Right? So p-norm, remember, we said it's very nice because we would like to normalize minimize p-norm, but we cannot do it for single machine. But now, if I permit resource augmentation, I can do it not just on single machines, but actually a heterogeneous cluster of machines. Right? So this idea, this tiny idea of resource augmentation, which has been around but somehow did not get applied to this domain, works wonders. So I will at this point realize that I'm running out of time. So I'll quickly skip a few slides, and I'll skip in particular the scheduling with rejection. In one word, remember there was also the stretch metric that I wanted to minimize. And we realized that the stretch metric cannot be minimized even with machine speed up. Okay? So even if I have faster machines, I cannot still work on the speed. I still cannot get an online algorithm for the stretch metric. So we came up with a new model where we said, okay, let's allow for rejection of jobs. And now we allow the online algorithm to not serve an epsilon fraction of the jobs. And you can choose your epsilon, whatever you want. You can say, I will allow my online algorithm to not serve 1% of the jobs. And this is reasonable in many settings, right? You send a request to a server which is overloaded, you get back a message saying, overloaded server, please come back later. And that's the best one can do. So, even if you don't like it, one has to live with it. So, I'll skip these slides, which were motivating, and just jump straight to the conclusion. Apologies that I didn't plan this better. So, this is the theorem that I said in the rejection model. We can prove that, the fairly straightforward algorithm is roughly, now the computative bounds are worse, it's 1 by epsilon to the power 6. So, time to conclude. If we do not know about the future, and none of us do, but incorporating it into designing algorithms, or if you want to incorporate that into design of algorithms, then online algorithms are really one of the most powerful ways of doing it. Okay? The adversarial model is quite often critiqued for being too harsh. Right? That the adversary can do whatever it wants, and the online algorithm really has no power. And people have in the past tried to get around it by giving less power to the adversary or giving more power to the online algorithm by telling the online algorithm a little bit about what the future requests are like. There have been many, many models considered. Resource augmentation, both the two ways that I told you, machine speed up and job rejection, is one way of handling these issues, and it has had a lot of success, especially for scheduling problems. I'm thankful for an excellent colleague in Amit Kumar, and most of this work has been done with him, and 3 of our PhD students, all of whom have graduated. Thank you.